sometimes. I'm sorry, I don't know what it is.
So we'll return to talking about some more theoretical things about linear transformations soon, but the eraser is missing. Yeah, napkins again. That's going to be a little bit annoying. Okay, but for now we're going to do something it's very important, but it's going to be very computational for the moment. We're going to talk about eigenvalues and eigenvectors. They have many uses. We're not going to see all of them. You see like 2 or 3, but they're very useful in a lot of ways. Not only computational, which is how we're going to look at them, but as a theoretical tool, they're also very important things to talk about. So these are called eigenvalues and eigenvectors. So let me kind of tell you what the definition is. Then I'll sort of explain what that kind of means, and then I will also tell you how to actually find them, how to compute. So let a n by n square matrix be a matrix. And suppose x not equals 0 is in Rn. Or Fn, but we're thinking of Rn for the most part. Then x is called an eigenvector of A if you take A times that vector and you get lambda times the vector, where lambda is a scalar called the eigenvalue. Corresponding to x. Okay. So in other words, what does that mean? I.e., this is the eigenvectors are the set of vectors that are scaled by our linear transformation. But remain parallel. The eigenvalues are their scaling factor. So remember, we can think of matrices as linear transformations, and geometrically these guys have an interpretation. They can move vectors around in a plane and do stuff with it. You can use matrices to rotate things and project things. We saw a couple examples of that. So for example, if you look at the matrix 1, 0, 0, 0, we saw what that guy did. This was the guy that told us to project to the x-axis if we're in R2, right? That was the guy that noticed that, if you take A times x, which I can think of as this, times the vector xy, you just get the vector x0. So in other words, I can have a vector doing its thing over here, but then and that's my x, but if I multiply that by this matrix, boom, it projects that vector down here, and that's the new transformed vector AX. Okay? So we can think of these matrices again as linear transformation. There is a geometrical component to it. However, but what if your x was already along the x-axis? That's your x. What would your AX look like?
Same thing.
It would be exactly the same thing, right? It's actually not going to move, right? In fact, it's scaled by 1. I can actually make this a little bit more nuanced. What if A was something like 2, 0, 0, 0? And I'm looking at the vector x, which is going to be something going like the I vector. What would happen now? It's going to scale itself by 2, but it's going to maintain its direction. So this vector 2x is actually going to be equal to the AX vector, right? So it maintains its direction. It stays parallel to what it originally was, but it's scaled by some factor, right? So what I can say, for example, is the vector I is an eigenvector of this matrix. Its eigenvalue is 2, right? So it is a vector that is only scaled by this linear transformation, and its scaling factor is 2, right? I can say a similar thing for here. I could not say that about any vector that's not parallel to the x-axis, though. If I take any vector that's not parallel to the x-axis, hit it with this guy, it completely changes its direction, okay? So I can say any other vector that's not parallel to this is not an eigenvector of this matrix, okay? So these are, I'm looking for the sets of vectors that they don't change their direction. They might in fact, like if I did this, it might in fact go in the exact opposite direction, but it's still going to be parallel to its original direction, and it's going to be scaled by some factor. It's very important to be able to find these vectors. Yeah?
When you project onto the x-axis, it's not 1, 0, 0, negative 1.
For what? If I'm looking at this
For
one?
One is in that case, yeah. When it's x negative y.
It depends on what vector are you talking about. What vector are you talking about? Give me an example of a vector that you're talking about.
I think she's talking about the transformation that's 1, 0, 0, negative 1.
Okay.
Would be reflecting over the x-axis.
Oh, if there's a negative 1 here, yeah, that would map it down here.
Yeah.
Yeah, but this vector still wouldn't be an eigenvector. It will still completely change its direction. This one would still be an eigenvector of that transformation as well. Right, but if you look at something like 1, 0, 0, negative 1, and if you multiply that by xy, right, then the result of that would be x minus y. So it will take something that looks like this and it will map it down here. Right? But again, anything that's parallel to the x, it's actually not going to move again. So the I vector is still an eigenvector of that. But that's the idea. We want these vectors that they don't change, they don't drastically change their direction once we hit them with the linear transformation. They're only scaled by the linear transformation. Such vectors are called eigenvectors. Their scaling value is called eigenvalues. These are very important that we can find these vectors. More important that we're going to realize by the end of this course, because in one semester of linear algebra you can only do so much. But how do we find them is going to be one important thing. And then we're going to use them to do so. So how do we find them? How do we find these guys? How do I know which set of vectors will only be scaled by a linear transformation? Notice that we want this to be true. We want a times x to be a scalar times x. In other words, I can subtract ax from both sides. Get the 0 vector on that side. And I can factor out my x. It stays on the right because matrix multiplication, not commutative. So I end up with this equation, right? Now, of course, x equals 0 solves this. But we want other solutions. Right? X equals 0 is the trivial solution. It's not going to, no point in finding x equals 0. We don't really have any information. Right? That's the guy that points everywhere and nowhere. We want some guy that's non-trivial. For example, I would want to be able to, for this vector, find the fact that I is one of such vector. How would I do that? Right? So here's a linear, here's a matrix equation. How do I ensure that it has more than one solution? Yep.
I mean, if the trivial solution exists, then if the determinant is 0, then
Exactly. Right? If you have ax equals b, if the determinant of this guy is not 0, we have a unique solution. So if I want other solutions other than the trivial solution, it must mean it must have infinitely many solutions, which means I want to force the determinant of the coefficient matrix to be 0. So I need the determinant of lambda I minus a to be 0. And that's going to give me more than just the trivial solution. Right? If the determinant is 0, there's only the trivial solution. And so that gives us an equation that we can solve for lambda. Notice we're taking a determinant of a matrix, so that's just going to be some scalar, right? It's going to be a scalar in terms of lambda, so it's going to be an equation. And I can solve that equation for lambda. Once I have that lambda, I can plug it back here and solve it for x, right? So by solving this, ultimately I'll be able to find the eigenvalues first and then find the corresponding eigenvectors second. Right? This guy is called the characteristic equation. For A. Or you might see it referred to as a characteristic polynomial, because if your matrix has real entries, it's always going to be a polynomial over the field. Characteristic polynomial. So that's going to be the idea. So this here, let's call that equation 2. This here call equation 1. So here's the procedure. Solve equation 2 for lambda. These are the eigenvalues. 2 for each lambda. Find its corresponding x solution in equation 1. This will be its corresponding eigenvector. Let's do an example. I'm going to give you a matrix. -5, 2. It's a 2 by 2 matrix, so this is a matrix that's going to operate on R2 and output other vectors in R2, probably doing all sorts of things with them, like rotating and projecting and doing all sorts of stuff. But I want to find the vectors that are only scaled by this linear transformation. So given that matrix, find its eigenvalues and corresponding eigenvector. eigenvectors. So here's where we're going to jump into it. We're going to start with equation 2, solve for lambda, plug that into equation 1, solve for the corresponding vector for that lambda. So we need the determinant of lambda I minus a to be 0. In other words, I want the determinant of lambda 0, 0, lambda minus the a to be 0. In other words, I want the determinant of lambda plus 5 minus 2 minus 2 lambda plus 2 to be 0. And usually you can just jump to this step. You don't have to show this, but that you're clearly going to just take lambda minus this, lambda minus that, and the negative of those two. Or a similar procedure would form for bigger matrices, but that's what the 2 by 2 case is going to look like. And so what that means is how I find the determinant of this.
Lambda plus 5 times.
Yeah, this times this minus that times that. Lambda plus 5 times lambda plus 2 minus 4 equals 0. Notice that here I have a quadratic that is lambda squared plus 7 lambda plus 10 minus 4 plus 6, right? So that's the characteristic polynomial for this matrix. Notice it's a quadratic. A 2 by 2 matrix will have a second degree polynomial as its characteristic equation. And 3 by 3s will have, right? Because you're multiplying, you'll end up multiplying along the diagonal at some point. And you'll get, the power of lambda is going to be actually the number of rows in your matrix. But anyway, let's continue. That's our characteristic polynomial. So let's solve it. So what are we going to get? What is the solution to that? Negative 1 and? Okay, so that factors into lambda plus 6, lambda plus 1. And so I have one lambda value is minus 6, the other lambda value is minus 1. So these two values here are my eigenvalues. Now let's find the eigenvectors. Again, we're going to do that one at a time. So let's start with the eigenvector for lambda 1 equals minus 6. So what I'm going to do is I'm going to go back to the original. Remember, I want lambda I minus a times x equals 0. So I'm just going to plug this in. So in other words, that means I want lambda plus 5 minus 2 lambda plus 2 times x equals 0. So in other words, now I'm going to plug in minus 6 for the lambda. Augment that system because I want to solve that system for the vector solutions. Plug in minus 6 here, I get minus 1. Plug in minus 6 here, I get minus 4. That's 1, 2, 0. That's row 1 times minus 1. And if I take row 2 minus 2 row 1, notice that all gives me zeros. So that means my x2 is going to be t, and I know that my x1 would be minus 2t. So in other words, my x1, x2 is going to be minus 2, 1. See that vector here? This is the eigenvector corresponding lambda 1 equals minus 6. In other words, what I'm saying is every vector that is parallel to this vector will be scaled by -6 when I apply this linear transformation. So all vectors in this direction, hitting it with the linear transformation is going to stretch it by 6 and literally flip it in the opposite direction. It's going to stay parallel to its original direction, but it will be scaled by a factor of 6. And I don't think this is official notation, but for shorthand, I'm going to call it λ1 vector. Okay. And you do this for the other one as well. So for λ2 equals -1, I'm going to do the same thing. I'm going to plug in -1 here. That's 4. -2. -2. 1. And so that's going to be -2, 1, 0. That is going to be 0, 2. So what I can do here is take row 1 plus 2, row 2. That'll be 0. 0, that'll be 0. So here again, my x2 equals t, and I know now that minus 2x1 is equal to minus x2. So this means that x1 is equal to 1/2 t, which means my x1, x2 is going to be t times 1/2 1, which any vector parallel to this can work, so I'm just going to scale this by some other scalar so that I can double these guys. There's my second vector. λ2 vector. So this linear transformation has 2 eigenvalues, 2 eigenvectors. Right? All vectors parallel to this will be scaled by -6. All vectors parallel to that will be scaled by -1. Every other vector in the plane is going to be doing something radically different, pointing into a completely different direction. It will not remain parallel to itself after being hit by this transformation. These are the only 2 directions that will be scaled by the transformation. In other words. So that is those are the eigenvalues and eigenvectors.
Jhevon, is the solution for λ1, the eigenvector we got for the solution for λ1, specific to scaling by -6 for vectors parallel to the solution?
Yes, they have to pair off.
Okay.
So this direction,
Okay.
they have to correspond. So yes, these vectors will be scaled by that factor, and vectors parallel to this will be scaled by that factor. You can't scale, these won't be scaled by -1. They do have to pair up. Yes. Yeah, that's why I keep mentioning corresponding. They do pair up. So you can't scale them by whatever you want, or scale anyone by any scalar. They do correspond. So vectors in this direction will be scaled by a magnitude of 6, specifically 6. And vectors in this direction will be scaled by a magnitude of 1, specifically 1. They won't be scaled by something else. Yeah. Yeah, so they have to correspond.
So
Yes.
when you write the answer, do you just like write λ1 vector is this, and then λ2 vector?
Yeah. You can say eigenvalues are λ1 equals -6 and λ2 equals -1, and eigenvectors. And you can mention correspondings to let me know that you know they have to correspond. And label it similarly so I can know that you're corresponding them, or otherwise indicate that this one pairs with that. And then that's how you would write down the answer. Now, as I said, there are many uses to being able to find eigenvalues and eigenvectors. We are going to look at two of them. So we're going to look at two applications here. An application of all this brings us to actually the next section called diagonalization. So let's start out with some definitions. There are a lot of them, but we're not going to use all of them. So I should define similar and diagonalizable. So definition. A matrix B n by n is said to be similar to A n by n if B is equal to P inverse A P for some invertible matrix P. Note. Of course, if it's invertible, you can multiply this side by P and that side by negative P and literally write the flip side of this. And so if B is similar to A, then A is also similar to B. If it works in one direction, it will work in the other direction. So that's the definition for similar. Another definition. A n by n is called diagonalizable if it is similar to a diagonal matrix. Remember what diagonal matrices are? Those are the guys that the only non-zero terms show up on the main diagonal and there's zeros everywhere else. That's what's called a similar matrix. So this is when two matrices are similar, means you can express one in terms of the other in this form. And to say something is diagonalizable means you can express it in this form with a diagonal matrix. P is set to diagonalize A, that's just a calculator. I think that's straightforward. Okay. Here's a theorem that's going to be nice, and then I'll tell you some other nice properties. Theorem. Let A n by n be a matrix. Then the following are equivalent. Meaning they will both happen at the same time, or they will both not happen at the same time. Equivalent. 1, A is diagonalizable. i.e. A is equal to P inverse. Sometimes it's nicer to write this way. B is diagonal. And 2, A has n linearly independent eigenvectors. So if you have an n by n matrix and you can find n eigenvectors and they're all linearly independent, it means that A is diagonalizable. There exists some diagonal matrix that you can make it similar to. Another thing about eigenvalues and eigenvectors is that if you take the eigenvectors of a matrix, you can use them to form a subspace. And they actually form a basis for what we call the eigenspace. So in other words, this is kind of saying that if the eigenvectors of your matrix are actually a basis for the space that it's in, it will be diagonalizable. Or you say that the space has an eigenbasis, which is like a second semester linear algebra course you can talk about that. But that's kind of where it's going. But we're not going to go that deep into it. Okay? But knowing that we can find n linearly independent eigenvectors means that there is a diagonal matrix for which this is true. In fact, we actually know exactly what it is. In fact, we know what these will look like. Let A n by n be a matrix. And lambda 1, lambda 2, lambda n are its n linearly independent eigenvectors. If they exist, it doesn't have to. If they exist. So suppose they exist. We have a matrix and it has n linearly independent eigenvectors with corresponding eigenvalues, lambda 1, lambda 2, lambda n. There's no intrinsic order here, but when you order them, it will matter. The order will matter. They have to line up. Okay? Then, it turns out, P equals this guy will diagonalize A. You literally take the eigenvectors and put them as columns. Turns out if you make the eigenvectors the columns of a matrix, that n by n matrix will actually diagonalize A. It will operate as this matrix out here. And it will make it similar to this particular diagonal matrix. Can you guess what's going to be in the diagonal matrix? We already used the eigenvectors, so it turns out it's going to be the eigenvalues. If you put all the eigenvalues on the diagonal and line them up in the same way that you lined up their corresponding eigenvectors, there's lambda 1, lambda 2, all the way down to lambda n, with zeros on the other side. So once you're able to find n linearly independent eigenvectors for a matrix, you can actually make it similar to a diagonal matrix. With these two matrices in particular. It will also be the case that none of the eigenvalues would be 0. So these will all be non-zero numbers. Turns out if one of your eigenvalues are 0, then you won't have any linearly independent eigenvectors. that's kind of an if and only if thing. But yeah, we can make a matrix similar to a diagonal matrix provided it has n linearly independent eigenvectors, and we can use these two matrices to make it so. You'll notice that in our example, I gave you a 2 by 2 matrix and we found 2 eigenvectors. And it's easy to check that they're linearly independent. I'm actually going to construct I'm going to diagonalize that matrix for you. But one thing, why do we care? There's a couple reasons, but I'm going to tell you one of them. Why do we care? Similar matrices share a lot of properties. They have a lot of things the same. They'll have the same rank, they'll have the same trace, they'll have the same Eigenspace, they have the same a lot of things. In other words, when you have two similar matrices, in many respects, studying one of them is the same as studying the other one. And diagonal matrices are notoriously easy to deal with, right? You can find their determinants pretty easy, just multiply along here, right? You can also find their inverse pretty easily, just take the reciprocal of all these guys here. You can find their powers very easily, just raise each value here to the power, right? So algebraically, working with the diagonal matrix is super easy. And because if I can write any matrix as similar to a diagonal matrix, it will maintain a lot of the properties that the original matrix has. So actually studying this guy is the same as studying the original guy. So what I can do is, if I have this linear transformation that I want to study, and I can find its eigenvectors, I realize that they are n linearly independent one of them, I can create an eigenbasis, shift my space to look from the perspective of eigenvectors, and that matrix will transform into a diagonal matrix. I can then do anything I want with this diagonal matrix, which will be a lot easier, and then the answer will always translate back by taking this matrix P. Right? So it's kind of like I do a change of basis. This is kind of like a change of basis to change into the eigenbasis. And once you do that, your matrix will now change into something like this. So that's very useful. I know that in the next section is when we do powers. No, in the next section we're going to actually use it to solve differential equations. In this one, we're going to use powers. So let's actually do that. So let me do an example so you can see. And you can check this on your own. I'm pretty much going to write down the answers and you can verify them. It's going to be 2 by 2, so it's going to be easy to verify. Having our talk on Thursday, I'm super excited. I told him I think my class would be very interested to hear you talk about half the reason because I went. Because sometimes you teach the theory of something so much, sometimes you actually want to see how it's applied in real life, and it's nice to actually get the perspective of someone who actually uses it. So here's the example. It's the same matrix as before. So it could be something like this. So the problem could be something like diagonalize A. Equals -5, 2, 2 minus 2. So it's going to ask you specifically to find the matrices P and D. By finding matrices P and D so that A is equal to P times D times P inverse. Okay. So what you would do is, if that's the problem, right? So you get a problem like that, you see it on a test or a quiz or a final or something like that. So it says, diagonalize this matrix by finding these two matrices so that you can write A as that matrix. A product of those three matrices. So what you do is you'd immediately do what we did before to find the eigenvalues and eigenvectors. So we know that lambda 1 equals minus 6 and lambda 2 equals minus 1 are eigenvalues, and lambda 1 vector, lambda 2 vector are the corresponding eigenvectors. What were these guys? 2, 1. Negative 2, 1? Negative 2, 1, and 1, 2. So this means take P to B, and they're going to take these two guys and put them as the columns. Minus 2, 1, 1, 2. And take D equals, it's going to be 0 here and here. On the main diagonal, I'm going to line up the corresponding eigenvectors. So the eigenvector in the first column has to correspond to the eigenvalue in the first row. So that's going to be minus 6, and then minus 1. And you can check. You will be able to write this matrix as minus 2, 1, 1, 2, minus 6, 0, 0, minus 1, times minus 2, 1, 1, 2 inverse. You can actually do that, and you'll see that is true. What's the inverse of the 2 by 2? It's 1 over the determinant, right? Which is minus 4 minus 1 minus 5. And then you switch these on the main diagonal, and then you negate those guys. So you can actually do this. You can take minus 1/5 of minus 2, 1, 1, 2, minus 6, 0, 0, minus 1, and 2, minus 1, minus 1, minus 2, and you will get this matrix. And that's very useful in a multitude of ways. One, it means that we can study this matrix, and it's pretty much similar to studying this matrix. This will maintain a lot of the properties. A lot of properties will be invariant under an eigenbasis change. And so doing stuff with this guy is the same as doing stuff with that guy. I'm going to show you one particular case in which it makes things easier. I'm not going to ask you about the things that it maintains, but I just want you to have the appreciation that that's what's going on. This is why we might want to do this. It will maintain a lot of the properties of a linear transformation that we care about. And you can even try to look. Notice that the trace of this is minus 7, the trace of that is also minus 7. A lot of things will be the same. You'll be surprised. Anyway, so here's an application of this. Let's say I want to repeatedly multiply this matrix. Find a to the 1,000th power. That's super annoying, right? But finding this to the 1,000th power, sure, the values are going to be big, but it's not going to be annoying computation speaking. That's just going to be 6 to the 1,000, 1 to the 1,000. Okay? But this guy, you can't just raise each thing to the power. It doesn't work. It only works for a diagonal matrix. But let's say my A, I can write A as P, D, P inverse. Then it means if I take A to the kth power, where k is some positive integer, what that means is I'm multiplying this guy by itself. K times. What's going to happen? The P, all the P's on the interior will cancel out. I'll be left with K D's in the middle, and then the P's on the end. So I can literally raise it to any power by just raising the entries on the diagonal matrix to a power and multiplying both sides. So instead of multiplying a matrix by itself 1,000 times, I can literally take the product of 3 matrices. So, for example, I might ask you on a test, compute this to the 50th power. And I'm going to see who was paying attention to try to find a pattern. But the idea is you can actually do this pretty easily by knowing you can diagonalize it. It's not actually that bad. So this is one of the ways, a very trivial way, but significant nonetheless, if multiplying matrices is something you're going to have to be doing a lot of. Notice that since minus 5, 2, 2 minus 2 is equal to minus 1/5, minus 2, 1, 1, 2, minus 6, minus 1, 0, 0. 2 minus 1, minus 1 minus 2. This means that if I take this guy to the 50th power, it will be the same as taking this to the 50th power. So that'll be 6 to the 50, 0, 0, 1, 2 minus 1, minus 1 minus 2. And you multiply those 3 matrices, that's the same as taking the 50th power of the original. Let's look at another application. This brings us to section 5.4, where we're going to talk about linear differential equations. Now I know some of you have taken or are taking differential equations, so you'd be very familiar with this subject matter here, because we're only going to look at first order. But I guess I can just do a quick little, it's not meant to be comprehensive at all, but just a quick little explanation of the kinds of objects we're going to be studying here. So a first order linear differential equation is an equation of the form y prime equals, say, p of y. You can make this a little more general, but I'm specifically going to care about ones that pass through the origin, where their solution passes through the origin. So the idea is A differential equation is just an equation that involves the derivatives of a function as well as the function itself. Okay? And so we can say it's a first order differential equation if there's only the first derivative that it's involved. You can emphasize that it's an ordinary differential equation because it's an ordinary derivative, not a partial derivative. So if I'm looking at single variable functions, we call it ordinary differential equations. But if I'm looking at the equations that involve both derivatives of a function and itself, that is called a differential equation. And when you have this form, it's a very trivial first order linear differential equation. You'd have seen equations like this before, I assume. Calc 1 is probably where you have seen some of this in the first place. That is this is an equation that is the models population growth for 1. Right? So if your y is a population, populations tend to grow. A very naive model is that the population will grow proportional to its current size. So its rate of change is proportional to its current size. The more people there are, the more babies they have. The population grows faster when there are more people. That's a very basic idea that can be captured with such an equation. Differential equations, super useful. Applicable to a lot of scenarios, and first order differential equations are one of them. One class of these equations. So to solve a differential equation, so usually when you have a differential equation, that you're measuring something and you just measure it in terms of rates of change, you end up with a statement that has a rate of change in it. But sometimes you may want to make a statement about the function on its own without talking about its rate. So to solve this equation, you need to basically eliminate the derivative. We need to find a function y equals, say, just some function of t that makes it true. So basically find the function that when you plug it in here, it makes sense, is called solving the differential equation. So for example, y equals e to the p times t. P is a constant. P is a constant. We'll solve this differential equation. Notice that if I take the derivative of this, derivative of e to the pt is p e to the pt, right? Notice that if I take y is equal to e to the pt, if I find y prime, that's going to be p e to the pt. But notice that this guy here was just the original function. So this means that my y prime is equal to p times y, right? So this function actually makes sense when I plug it into that equation. In fact, any constant multiple of this function will make sense. So I can put c e to the pt. This is an example of a solution to the solution. Taking differential equations, you'll learn that this is literally the only solution. And the argument there is actually a linear algebra argument, but let's not talk about that. This guy here is called the general solution. To this differential equation. So you have equations like this. You want to solve them by finding a function that has no derivatives involved. It's just, I'm just measuring the function in terms of some other, the input variable. And once I can plug it into this and it makes sense, I say, oh, I found a solution. Notice that, for example, y equals x squared is not a solution, right? Because if I take x squared and I find its derivative, I don't get p times it. Okay. So that's something that we'd call a first order linear homogeneous equation. And you can have non-homogeneous ones, but we won't care about this. So here's the scenario. Suppose you're measuring more than one thing, and you come up with a bunch of these guys, and they kind of intertwine with each other. Now we're into something that it's going to take some linear algebra to study. So suppose we now have a system of such differential equations. say y1, I have two functions, y1 and y2, and say I could measure the derivative of y1, and I can write it as a sum of the functions y1 and y2. And I can have another function y2, and its derivative I can express as a linear combination of the functions y1 and y2. So I have two quantities, and their derivatives can be expressed as a linear combination of the original quantities. So now the question is, how do we solve this? And the answer, unsurprisingly, is with eigenvalues and eigenvectors, because that's what we're talking about. So notice that we can write this in matrix form by saying if I set y prime vector to be y1 prime, y2 prime, the y vector to just be y1, y2, and then take A to be the coefficient matrix. We get this sort of equation. Y prime is equal to A times Y. We want to solve for Y. Right, similar to we have this, we want to solve for the Y. Right? But here it's more general. They're vectorized, and we have a 2x2 system. Okay? I'm just going to tell you the solution. Here's the solution. Let lambda 1, lambda 2 be the eigenvalues of A. With corresponding eigen, those are eigenvectors. With corresponding eigenvectors, lambda 1, lambda 2. So say you have this coefficient matrix, you can find its eigenvalues and eigenvectors, and there are n of them. Then, here's what the solution is. Y will be equal to, just as there's some arbitrary constant here, we're going to have them here as well. We're going to have two of them. C1, lambda 1 vector, e to the lambda 1 t, plus C2, lambda 2 vector, e to the lambda 2 t. That's your answer. That will solve this linear system of differential equations. Let's actually do an example, and I'll leave the verification to you on your own time, but I'll tell you what you might have to verify. So here's an example. So it's not a regular linear system of differential equations. Now we have calculus involved, there are first derivatives involved. So I can ask you, for example, to solve the system y1 prime is equal to minus 5y1 plus 2y2, and y2 prime is equal to 2y1 minus 2y2. And notice that these guys are all functions. So these are functions of t here. So they're not, these are all functions of t. So y1, y2 are functions, are single variable functions of t is what we're calling the independent variable. Because a lot of times when you're doing differential equations, you're thinking in terms of time. Right? You're measuring rates of change. So here's a system of differential equations. And that they write coefficients that I minus 5, 2, 2 minus 2. Yes, okay. So that could be a problem. Solve the system of equations. You'll realize, hey, there are derivatives here. So it's a system of differential equations. They're linear. And so what you can do is, we see here that our A vector is minus 5, 2, 2 minus 2. And that's the same guy that we found the things for earlier. Our lambda 1 was minus 6. Our lambda 2 was minus 1. Our lambda 1 vector was minus 2, 1. Our lambda 2 vector was 1, 2. It's minus 2, 1, right? This means that to solve for y, the answer is going to be C1 times minus 2, 1, e to the minus 6t plus C2 times 1, 2, e to the minus t. That's actually the answer. Let me express it slightly differently. Something that's more verifiable. No, this means that the function y1 is actually minus 2c1 e to the minus 6t plus c2 e to the minus t. And the function y2 is going to be c1 e to the minus 6t plus 2c2 e to the minus t. So it turns out these two functions are linear combinations. And you can actually check that, take the derivative of this guy and then compare that to minus 5 times this plus 2 times that. You'll notice that you actually got the derivative. If you take the derivative of this guy, it will actually be the same as taking 2 times this minus 2 times that. You can verify that pretty easily because taking derivatives of exponential is not a big deal. But that's the solution. One other thing we can talk about here. Sometimes we are given initial, so-called initial conditions. Right? This is just the value of the function at some point. So for example, if I wanted to say something like, okay, y prime is equal to 5 times y, right? But I tell you the function that I want is the one where when my t is 2, the output is, when my t is 0, the output is 2. So I give you a differential equation, but I also give you what we call an initial condition. Some condition I want that to hold. Notice that you can solve this guy. You know that your y is going to be c e to the 5t, right? Differentiate this, you get 5 times the original. But this gives you an infinite number of solutions, right? This gives you a family of solutions. For every c you plug in, this will solve that. But I don't want the entire family. I want one of them, one specific one, the one that passes through the point 0, 2. And so what you can do is, so this guy here is your general solution. But we want this is what they call it, the particular solution. And all you have to do is just plug this point into the answer that you just found, solve for the arbitrary constant. So if I say y of 0 equals 2, this basically means that my y value is 2 when my t value is 0. And so this would mean that c equals 2, and so this would mean that I can solve specifically the function that solves this differential equation passing through that specific point is going to be 2e to the 5t. Notice that if I take the derivative of that, it's going to be 5 times itself. Moreover, it is a function that passes through the point 0, 2. So this is called the particular solution. Sometimes we want to have conditions on this one. And so I just gave you a general solution, but we might want the particular solution. I might want to talk about the functions y1 and y2 that pass through 2 specific points. So now suppose in the above, by the above I'm talking about this question here. We are given y1 of 0, y2 of 0. So I told you 2 initial values for these guys. Write them down. Let me just make something up. Let's say this was 2 minus 1. It's going to have a solution because the determinant of the coefficient matrix wasn't 0. So hopefully it's not too bad. And so what this means is we can actually go here and start to plug these in. So I can set this equal to 2, plug in zeros for the t's, and I would get 2 is equal to minus 2c1. Plus C2, and I can set minus 1 is equal to C1 plus 2C2. That's just a regular old system of equations, huh? And so call this equation 1, call this equation 2. What I can do is something like take 2 times row 2 and add it to row 1. So 2 times this plus that, 0, 2 times this plus that, 0, 2 times this plus that is 5c2, which pretty much means your c2 equals 0, which pretty much means your c1 equals minus 1. So in other words, the set of functions that solve this system of differential equations, where each individual function passes through these 2 points specifically, is going to be these 2 functions. This means y1 equals, I'm going to plug in c1 equals minus 1, 2e to the minus 16, c2 equals 0, minus e to the minus 16. And that is my particular solution. That's all we need to know about eigenvalues and eigenvectors in this class, but that's really not even skimming the surface. They're very useful things to be able to compute. And changing the basis to an eigenbasis is also very useful. But you can, first of all, we looked at how to find them. Notice that you can take powers of matrices easier. Also know that this can work in general. So for an n by n system, you just have the n eigenvectors are the coefficients, and then the corresponding eigenvalues are all the powers. So we can continue like that. But we'll stop there for now. I'll see you guys on Thursday. It should be a lot of fun. And leave your papers on the table here.
Are we having an exam next week? That's it?
I'll tell you on Thursday. We'll probably do another take home and then the final